Good morning, everyone. My name is Will Hasting. I'm a solutions engineer for Velo3D, and I'm excited to talk to you today about how you can accelerate metal AM adoption in your companies without having to redesign. So when I started off in metal AM, it originally was for an engineering consultancy, basically helping major Fortune 500 companies bridge the gap between their conventional designs, conventionally made designs, and helping transition those designs to additives. So there's many benefits that are touted. For instance, improved part performance, improved supply chain flexibility, lower time to market, lower NRE. However, when it came down to it, what I was finding is we'd have all these promises for the project at the very beginning, but we'd all of a sudden have to add supports, and it felt like supports were everywhere. Every angle lower than 45 degrees would have to have supports, or additionally, we would need to adjust the original design in order to make it printable. So all of a sudden, round surfaces had to be teardrop shaped to 45 degrees and so on. And the problem with all of these little compromises and tweaks is that starts to erode the value of the project that was the original business case to convert the design to additive. And really, though, this has caused this chasm to start to exist where we have a lot of metal AM designs that are stuck in this prototype phase because we can't make the business case to bridge the gap to production. And this is a key aspect because we're here to impact the world, the greater population. And if our designs are stuck in an R&D and in prototyping stage, we're not really able to unlock the benefits of metal AM to the real world. So I want to back up a little bit and dive deeper of why are we in this situation to begin with? Why do we need supports? So just an overview of the overall laser powder bed fusion process. So first off, we have a layer of powder for our machine at Velo3D. This is 50 micron layers. And then there's a solid metal substrate underneath that, or the part that's being printed. And so the layer by layer, the powder is heated up and melted. And then as it cools onto the layer beneath it, it actually causes a potato chipping effect. So it causes the shrinkage that you can see in the lower left side of the screen, and that accumulates layer by layer more and more residual stresses. So one solution to avoid this is to add more supports. It basically holds the patient down on the operating table while you keep printing layer by layer. The other aspect is as the angle gets lower and lower beneath 45 degrees, the process window becomes tighter and tighter. And so right here, I'm showing you some geometry, and I have the real part with me right here. You can see it's a 15 degree disc, and on the above top of the slide, you can see what happens when it goes correctly, when the process is done correctly. However, when the melt pool becomes unstable, what happens is that the melt pool will get too hot. It'll burn through the solid metal substrate underneath, and then start melting the powder underneath. And so by having supports in this case, it provides a heat sink as well as avoids the case of burning powder underneath. So it basically allows you it gives you guide or bumper rails to keep you from causing too much damage in the process. So there's two main concepts that have been used to overcome this phenomenon. So first off, we have just a hollow structure here, an arced structure. And you can see the design intent is to actually have that structure rounded off at the top. And so one solution for this would be to add supports to this structure. Another way would be to redesign it. So redesign meaning take that nice round structure that was meant to have fluid flowing through it or another purpose, and you actually have to teardrop shape this to 45 degrees to make it printable and have a nice surface finish. And this is generally known as some of the key concepts for design for additive manufacturing. But at Velo3D, our company mission is no redesign. And this is a fundamental shift because we're actually trying to minimize the amount of design for additive manufacturing techniques that you have to do day in, day out with your jobs. And what this helps do is this helps preserve the value of the overall project, of the overall part, to help make sure that the project is on track to meet performance targets as well as business case targets and other aspects to it. So besides the fancy PowerPoint graphics, I'd like to show you some real parts. So up here on the screen you can see the back-to-back comparison of a part printed conventionally, so that's with the supports here and on the above screen. And then you can see as well the Velo 3D solution where there's no supports on the inside of this part. So this is a radial impeller commonly used, and we actually end up printing quite a few of these because of our unique set of technologies. And we'll be at booth 360 as well, so if you'd like to look at these parts in more detail, feel free to drop by afterwards as well. So how does Velo 3D approach this problem? We have a fundamentally different way to approach this problem, and the first part is tighter process control. We're controlling the laser powder bed fusion process. We're controlling the heat input in the melt pool far beyond what other conventional metal AM manufacturers on the market are doing today. And the other aspect is the non-contact recoater. And there's a key aspect to how the non-contact recoater helps us with these low angle geometries, such as the disc that I showed you a few moments ago. So as you print with lower and lower angles, then there's a tendency from the residual stress for there to be a slight bow up, that potato chip kind of phenomenon that I was just talking about. And by having a non-contact recoater that actually floats above the powder bed, it allows slight protrusions to occur, which is fundamental to being able to print at low angles. So for instance, with a hard recoater on a conventional machine, typically a protrusion on the order of 30 to 50 microns will cause a build failure in the recoater to clash. So we're talking about very small amounts of thermal deformation can cause catastrophic failures with conventional machines. But with the Velo 3D non-contact recoater, it basically gives you this protrusion tolerance to protrusions that allow you to go lower and lower. So now I'm going to talk a little bit more about the Sapphire configuration, because what I'm going to talk to you about today are design principles and this how to design with our technology, and this is fundamentally different than other machines on the market today. So first off, we have right here, this is the size of our build plate. So this is 315 millimeters in diameter. So that's about 12.4 inches or so. And then additionally, our Z height is 400 millimeters tall, so 315 by 400. And there's a key aspect to this as well, is there's no bolts on our build plate that are causing keep out zones. Because if you go back to the beginning where I'm talking about the dream and then the reality, it's like you have say a 250 by 250 build plate, and then all of a sudden you have to have keep out zones on the corners because it's bolted down. For us, we have a clever attachment mechanism for our build plate, so there is 0 keep out zones. Additionally, we have dual 1 kilowatt lasers that have complex configuration and in situ overlap and distortion correction that basically eliminates any sort of stitch lines. Next, right now we're printing in Ti-6-4 and Inco 718. Most of the parts you see up here today will be in Inconel 718, but we have some Ti-6-4 as well at the booth. And then additionally, we are currently working on aluminum F357, which will untap or tap into another market, especially in the aerospace fields. So now looking at more detail of the build chamber layout. So a couple of key things I want to talk about here as it impacts the design. First, for each laser, there's this ability to reach the entire build plate. So this can be an issue where sometimes with multi-layer systems, a laser can only handle one corner of the build plate. We've intentionally designed our system to be able to have both lasers span the entire build plate. And then additionally, we don't have any surface area per layer limitations. So this is another time where I've had some frustrations where you think you can use that entire build plate and you want to fit 50 parts on a build, and then you realize, oh wait, no, we only can fit 25 because if we put too many parts on the build plate, all of a sudden you start running into gas flow problems and soot contamination. We purposely redesigned our gas flow system to be agnostic to any sort of high surface area per layer situation. And then finally, as I said before, we really are empowering you to use those lasers in tandem by having this overlay capability. And we'll, if you stop by our booth 360 afterwards, you can see where we have parts that are taking up the full build volume, and you can feel with your hands, you can let the light reflect off of it, and you cannot determine where any stitch lines are on those parts. So quite impressive. A little bit too large to bring over here today, but I look forward to talking about those parts to you later. So now we're going to dig a little bit more into the how-to of this presentation, because this is all about how you can design and enable your parts with the Velo technology. And really, so we still have some design constraints that we're working through, and this is something that we continually update every, I'd say, month, 3 months, as we continue to push the boundaries more and more to reach that holistic goal of zero redesign. So the first question I'm often asked is, can I even use these parts for structural applications? And in reality, in the aerospace sector, most of the metal AM applications today are actually used in critical locations, high impact parts. And a key aspect to this is really the material properties. So you can see right here, we did a study with the Barnes Group advisors where we compared our material properties. These are the exact same values that we have on our data sheet, and we compared them to AMS specs for rot and cast properties. What you're seeing here is that the Velo 3D printed parts, tensile bars, are approaching rot properties, and if you look at the -3 sigma values, or the minimum material properties, it actually is slightly higher than the rot properties, just because we're seeing less variation compared to the AMS specs for rot and cast. And then this is a similar slide, but this is for Tie 6.4, and you can see we're actually even closer to the rot properties here as well. And the reasoning behind this is, one, we have very low porosity, less than 0.1%, approaching 0.01%, so very high material quality. And then additionally, due to the laser powder bed fusion process, we have a very small microstructure. So again, having the smaller grain size helps you with your tensile properties as well. So now let's talk, we talked a little bit about the function, let's talk a little bit about the form. So I had a question yesterday about the dimensional tolerances and for features of size. So this is it varies with the size of the feature that you're trying to print. So for small geometry, it's about 50 microns. But now if it's to a large part, then there starts to be an impact with the shrinkage of the material. And so that's where we start to use 0.2% when you get into larger and larger sizes that stretch the full diameter of the build plate. Next, I'm going to go through some specific geometries here. So you'll be able, as we walk through these following slides, you'll see that it depends as a function of angle what we're able to print. And part of this is because as you go to lower and lower angles, while preserving a 50 micron layer and a 1545 particle size distribution, you start to approach theoretical limits as to how thin you can print with your process. So the first thing we'll talk about here is thin pins. So we're able to actually print grass here, and you can see right here afterwards. I mean, it's even right here, it is difficult to see 130 microns because it's really approaching the thickness of a human hair. Additionally, just another application that's really key is with radial heat exchangers. So right here this is still one of my favorite parts that we've ever printed at Velo. It's about 200 to 250 micron walls, so that's about 8 thou to 10 thou. And you can see just a beautiful surface finish. But in terms of capability, we're actually able to go down to 150 microns. And so in terms of like heat exchangers, if you're having to print very thin fins, this brings a lot of performance to that. And the surface roughness becomes a very important aspect in heat exchangers design as well. And that's an area that I'll touch upon in a few minutes here. Yeah, the aspect ratio. So for the aspect ratio, because we have a non-contact recoater, we don't have issues with aspect ratios. We've basically been able to build extraordinarily high. There starts to become an impact if you grow very large sheets that don't have any cross-beam support. So for this example, for the radial heat exchanger, there's actually a spar, mid-span spar, because otherwise you'll start to have a thermal buckling effect of the sheets. So it's important. Certainly there's the Z height, which I believe is more on par with what you were asking. But additionally, you start to, if you get very wide sheets, then you start to run into thermal buckling issues.
Can we see?
Oh, sure. Just don't pass it around. I'm afraid it won't come back. If I were you guys, I'd walk off with it. It'd make a very nice ornament. I don't know if my wife would agree, but So next, I'd like to talk about tubes here. So first off, the importance with printing tubes is that they're actually a very difficult type of geometry to 3D print. And it varies with the orientation. The most difficult is in the horizontal fashion. And so for this kind of geometry, it's a 40 millimeter diameter, maximum diameter, and then a 300 micron minimum diameter. And then there's also now, if you're able to then slightly tilt the part by 10 degrees, all of a sudden that 40 millimeter diameter actually grows up to 100 millimeters diameter. So a really key aspect to orienting the part within the machine. Oh, and then one other aspect to this, we do have a turbo that we can show you in some very large diameters in our booth, just for feasibility's sake. I didn't bring them along with me, but feel free to stop by booth 360 to see those. Next, we have dome closures. So similarly to the large diameter tubes, we're able to print up to 100 millimeters diameter. And then horizontal spans, this is one that I'm particularly excited by because we're actually now able to print 0 degrees unsupported up to 10 millimeters. And the surface quality is really respectable from the samples that we've done so far. So this is really key because sometimes we have customers where instead of wanting to print small diameter tubes horizontally, they actually want to print squares, square channels, in order to not have to modify geometry that was originally designed to be fabricated assemblies or sheet metal fabricated assemblies, things along that nature. So next, we'll talk a little bit about surface roughness as a function of angle. And so it's yet another thing to take into consideration with the orientation of the part and the surfaces. So you can see right here, this is the part on the upper left. There's the build orientation and of how it's printed. And then we've cut it off the build plate and we flipped it on its side, and you're looking up in that bottom picture at the as printed surfaces. So these surfaces have not had any bead blast. This is literally as it comes out of the machine.
Did you say you cut it off?
Yes, so this part is printed like with the build plate similar to my hand, and then we wire EDM it off, and the numerals right here are actually facing downwards onto the build plate. So right now we have a plot with SA. And SA is a more stringent, this is what we use internally to measure ourselves. SA is a more stringent form of surface measurement than RA because it takes, it doesn't create a low pass filter of waviness that RA does. And there's other different aspects. So if you want to think of this in terms of RA, basically divide the numbers by 2 and you'll start to get on the same order of magnitude, especially at the higher numbers. So for RA, we're generally in the range of 8 to 10 RA in the very low angle surfaces, and then in the 2 to 4 RA range for when you get closer to 90 degrees. So in these next slides, you'll have to bear with me because we'll go a little bit deeper with some 2D plots of, or color mapping plots of where the danger zone exists when you get too low of angles. And there's a lot of different aspects that come into this, and really this is, the purpose of this right now is, I don't expect you to remember all of these numbers, but I want to start to change the minds of, instead of anything less than 45 degrees, I got to support it to, okay, there's actually some, I can print down to 10 degrees in certain areas, or sometimes based on geometry, I can print down to 20 degrees. So we'll walk through this, and it'll keep an open mind as to how we approach this. So first off, these are the kind of plots I'll be showing in the following slides. So on the left axis, you can see the Z height. On the x-axis, it's the angle. And then if it's red, we are pretty confident that that build's going to fail. If it's in the yellow, it's kind of in the, it's very geometry dependent, it's on the edge, and then green is you're clear to go. So a key aspect of printing low angles is how much is that surface constrained. So on the top, you can see an unconstrained horizontal, or excuse me, unconstrained plane at a high angle, and then you see on each side there's restraints. So in the upper side, you can see that we can print up to basically 20 degrees is the limit. If you look in the upper right here. However, if you start to have the supports, you can see there's less yellow here, and you basically are able to print down to 10 degrees unsupported, and it really basically takes you from 20 degrees to 10 degrees all at once. Now, this cone is a similar story. So we have a convex cone, so growing upwards, and then we have an inward growing cone, so a concave cone. And we'll actually talk about this with the impeller example in the following slides as well. With the outward growing cone, basically in about the 20 to 25 degree zone, it starts to get very questionable, very difficult to maintain stability of the build. However, with having an inward growing cone, if you think about that potato chipping effect again, the residual stresses will want to make it curl inwards versus trying to curl outwards if it's a concave cone or convex cone. So let's talk again about this radial impeller here. So there's two different options to orient this. One, there's just upside down like you see on the screen. And when we do this, you can see that there's a high probability of breakdown of the process. So you can see on the upper right, really, you're limited in the 20 to 25 degree angle when it's oriented like that. However, when it's printed like so I'd say right side up in my orientation of thinking, then you're able to really print on 10 degrees and below. And we're doing a lot of development right now actually on going down to 0 degrees when you get into this case of radial impellers, because it's a case we see quite frequently. and a lot of promising results. So that's why you see on this screen here where it starts to get feasible to go less than 10 degrees there. So one other aspect I'd like to just touch on, we did a full presentation yesterday about free floating parts, and this is a great opportunity to basically lower part costs, simplify supply chain, and improve throughput of the shop. And I won't bore you to death, the folks that came here yesterday, but there's a key guideline with being able to print free floating, and that is being able to start on a single point. So because the residual stresses, if you're going to have a free floating part, so this means a part that is literally not attached to the build plate, you can pull it out of the powder similar to a SLS process in plastics. It has to start at a single point, and that's because if there's 2 points that start when it comes together, the residual stresses will be too high and it will deform the part and cause a build failure. So it's very important, and there's a lot of design techniques that are employed when starting to design for free floating. So if you have questions about that, feel free to talk to me afterwards as well. So in conclusion, you now have a better insight of where the current state of the art is with Velo 3D technology. This is a leap forward in terms of flexibility of design versus the conventional metal AM machines. And the whole intent is to reduce or preserve part performance, reduce the amount of post-processing on your parts, and really being able to realize the dream that we all had when we got into metal AM at the get-go. So in short, if you're about to defam your part, please call me first, and let's keep it on track for design intent. So thank you very much. So any questions in the audience?
Which are the limitations for this technology? Which are one of the most challenging or limitations this technology has?
Okay, the question is, what is the most challenging limitation of this technology? So I'd say printing down to 0 degrees is really the most challenging, and also closing out horizontal tubes. So that's something that we're continually working on and have a lot of process development. The other aspect is with heat exchangers to continually go thinner and thinner and preserve surface roughness, because that's another application where metal AM is really starting to shine. And the more that we can make heat exchanger fins thinner and smoother, the more it can be competitive and overtake conventional metal AM heat exchangers. Any other questions? Good question. Okay, well, thank you, and please stop by booth 360 to talk more about Velo 3D's technology and what we can do for you. Thank you.